Hello and welcome to lesson 2. Before we start this lesson, and I'll be doing this before every lesson, what I'd like to do is to introduce you to some of the polymer processing operations that make the stuff that we use every day. We probably use, wear and eat products that these operations make without even really realizing it. So let's start today with textiles. I bet that every one of you watching this video is wearing, or perhaps at least owns, some item of clothing that contains synthetic fibre. So what I'd like to talk about today is how we make polyester yarn. Now, I use the word polyester in a very generic sense because, of course, polyester is a whole species of different molecules. When you see polyester on clothing tags, typically what they're talking about is polyethylene terephthalate. It's a condensation polymer, like I've shown on the board there, and it is the same polymer that is going to be used in, for example, Coke bottles or soda bottles. It's just a slightly different molecular weight that's used for the soda bottles compared to the yarns. However, there are lots of other polyesters. Polyethylene terephthalate isn't biodegradable. However, polylactic acid, which is another class of polyester, is. And so if we're thinking about trying to remediate some of the harm that's been done over the decades in terms of pollution, what we can think about is biodegradability, and polylactic acid falls into that category. So if we want to end up as yarn, we've got to realize where we start, and typically where we start from in these processes are chips of polymer, like I've shown there on the board. And so somehow we've got to convert chips of polymer into a very, very fine and very, very strong thread. So let's see how we do that, and it's with a process called melt spinning. Now, perhaps not unsurprisingly, melt spinning starts with an extrusion line. So there I've pictured on the board a single screw extruder with a pelletized feed, and that extruder will be conveying the pellets, it'll be melting the pellets and producing a relatively homogenized polymer melt. Now, one of the characteristics of single screw extruders is that the melt flow rate that comes out of them can be a little bit pulsatile. Not particularly, and in many processes this simply doesn't matter. However, for something like melt spinning, which requires a very precise volumetric flow, we need to stabilize this flow. And so the molten polymer is transported along a heated conveying line to typically a gear pump, and the function of this gear pump is to meter the polymer flow and to make sure you've got a precise volumetric flow rate. So this precisely metered polymer flow rate goes to a set of what are called spinnerets. Now you can imagine spinnerets by imagining a shower head. It's a device that has many, many holes in it, and out of those holes comes the fluid. Unlike a shower head, where you've got a very, very low viscosity fluid coming out and breaking up into droplets, out of a spinneret you've got a very, very high viscosity fluid which forms filaments. And these filaments are then drawn down. So, as these filaments are drawn down, they have initially very little orientation. I've put no polymer orientation there on the board. It's not strictly true because there's going to be maybe some degree of orientation due to the shear and extension within the die, within the spinneret dies themselves. But for the purposes of quantifying orientation for yarns, they're not really oriented at point A. Now remember, in the last part of the last lesson, we really made the link between how you process a polymer and how it develops mechanical properties, how you orientate those chains, how you increase the tensile strength of the material. And that's what happens next here. So, at point A, you've got a quenching airflow and you've got a frost line. Now that frost line, where the polymer sets, is some way below the spinnerets. So there is an option to draw the polymer extensionally there, and then to cold draw the polymer further when it hits a set of rollers downstream of the frost line, when the material is in its solid state. These rollers are called Godet rollers, and they accelerate the polymer from maybe 2 or 3 times whatever the velocity the polymer is coming out of the spinnerets at, to a great deal more than that. And so over the course of the Godet rollers, the yarn speed increases and increases and increases. And this has 2 functions. First of all, you're applying a uniaxial extension to the yarn, so they become a lot smaller in diameter and a lot longer. And the process of doing that, as we saw in the last part of the last lesson, will develop polymer orientation. Note the speed that these filaments are travelling at by the end of this set of Godet rulers, 2.5 kilometers a minute or 150 kilometers an hour. These processes process very quickly. So you can imagine what would happen if you got a bearing failure on one of these Godet rollers and it all went slightly awry. There'd be a lot of yarn everywhere. Now, partially orientated yarn is actually a product that's used in the textile industry. But there's another product that's also used, which is fully orientated yarn. So we need to go from this partial orientation state, which is moderately strong, to a full orientation state. So there's one further processing step that can sometimes happen. And that involves reheating the polymer up to somewhere around its glass transition temperature, and then drawing it again in this hot state. So you've got a cold drawing stage, followed by a hot drawing stage. Now, the polymers can be heated in a number of ways, one of which is radiatively, and we'll be talking about radiation heat transfer in lesson 6. And what we have now is a further acceleration through this hot drawing stage. So the fibres leave the Godet rollers at point B at maybe 2.5 kilometers a minute. By the time they reach the take-up spool, they might be travelling at 6 kilometers a minute, which is really quite phenomenal. And there's a huge orientation increase from point B to point C, which imparts a great deal of tensile strength to these fibres. So there you have it, melt spinning to produce polyester yarns. Now, if you'd like to see this process in action, I put a link there on the board to a YouTube video showing a lab scale or pilot scale version. I'll also put that link in the show notes such that it's easy to follow, and I hope you enjoy that video.